Alright, EP Stat students, this is 5.3 where we start talking about conditional probability and independence. So remember our pierced ears example from our last one? Well, here's the idea of conditional probability. If we know that a randomly selected student has pierced ears, this key, we know this. What is the probability that the student is male? Well, we know they have pierced ears, so we're only looking at this column. Well, the probability that they're male is 19 out of 103. Because we don't care about any of these people that do not have pierced ears. If we know that a randomly selected student is male, what's the probability that the student has pierced ears? In this case, we know that they're male, so the probability that the student has pierced ears is 19 out of 90. Sounds just like that conditional probability. Remember we had marginal and conditional from way long ago? It's the same thing. Do these questions ask the same thing? No, they ask very different things because the thing that we know is different. The probability that one event happens given that the other event is already known to have happened is called a conditional probability. Suppose that we know that event A has happened. Then the probability that event B happens given that A has happened is denoted with that line. So this is read, probability of B given A. Students at the University of New Harmony received 10,000 course grades last year. The two-way table below breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering and physical sciences, and health and human sciences. College grades tend to be lower in engineering and the physical sciences, EPS, than in liberal arts and social sciences, which include the health and human services. Consider the two events E, the grade comes from an EPS course, and L, the grade is lower than a B. So we want to know the probability of L. This is the probability that the grade is lower than a B. Well, we need some totals first of all, so let's add some totals. Now that we have our totals, we can find the probability that the grade is lower than a B. So this is 3,656 out of 10,000. Then we want to find the probability that the grade comes from an EPS course given that it's lower than a B, and the probability that the grade's lower than a B given it comes from an EPS course. Which of these conditional probabilities tells you whether this college's EPS students tend to earn lower grades than students in liberal arts and social sciences? Well, the probability that it comes from the EPS, given that it's a lower grade, is 800 out of 3656. The probability that it's a lower grade, given that it comes from the EPS, is 800 out of 1600. Well, we're trying to find out if the EPS students tend to earn lower grades than students in liberal arts and social sciences. So we want to compare this one to the other ones. We would like to know the probability that it's a lower grade in the other places compared to the probability that it's a lower grade from the EPS. So this is the one that we want. We don't really care that it's coming from the EPS. If it's given in the EPS school, then we can't compare it to the other schools, so that's why this is the one that we want. Two events A and B are independent if the occurrence of one event has no effect on the chance that the other event will happen. In other words, event A and B are dependent if the probability of A given B is the probability of A, and the probability of B given A is the probability of B. So if one event occurs, it will not change the probability of the other. We want to find out if these events are independent. So if we shuffle a standard deck of cards and turn over the top card, we put it back in the deck, shuffle again, and turn over the top card. To find the events, A is the first card as a heart, and B, the second card as a heart. Well, since we put that top card back into the deck and shuffle, if that first card is a heart, it's not going to affect if the second card is a heart. So this is going to be independent. But we can prove it with the formulas. The probability of A given B, well, given that the second card is a heart, what's the probability of the first card being a heart? Well, it's the same because we put that back in the deck and shuffled. If we were to shuffle a standard deck of cards and turn over the top two cards one at a time, and we define the events the same, now we're going to have some issues. So if the probability that the first card is a heart, given that the second card is a heart, well, if the second card is a heart, then the first card only has a 12 out of 52 chance of being a heart because we already had one, which is not the same as the probability of getting a heart, which is 13 out of 52. So this is not independent. The 28 students in Mr. Tabor's AP Stats class completed a brief survey. One of the questions asked whether each student was right or left-handed. The two-way table summarizes the class data. Choose a student from the class at random. The events of interest are female and right-handed. So suppose we choose two students at random and look at their handedness. So we have our first student, which can either have a right hand, be right-handed, or left-handed. The probability of the first student being right-handed is 24 out of 28. And then the probability that the first student is left-handed is 4 out of 28. Well, then we have our second student. So given that the first student's right-handed, the probability that the next student is also right-handed would be 23 out of 27, because we have one less student. But the probability that that second student is left-handed would be 4 out of 27, because we have one less student, but the first one was right-handed. Then if we went down this path in our tree diagram, given that the first student was left-handed, well, the probability the second student is right-handed is 24 out of 27. And then given that the first student is left-handed, the probability that the second student is left-handed is only 3 out of 27. So that's how a tree diagram works. Find the probability that both students are left-handed. Well, this works by following this stem, this probability, and this one because they're both left-handed. The probability that the first one is left-handed and the probability that the second one is left-handed given that the first one was left-handed. So this is 4 out of 28 times 3 out of 27. So this leads us to the general multiplication rule. The probability that events A and B both occur can both be found using the general multiplication rule. So this is what we just used. This was the probability that the first person was left-handed and that intersection, the probability that the second person was left-handed. And you can see that that follows really nicely from our tree diagram because that second one depended on the first one. So we have the probability of A and B is the probability of A times the probability of B given A. This is that second branch on the tree. If the two events are independent, we get this. Notice the difference is the probability of B does not depend on A, because remember the definition of independence. If the probability of B given A equals the probability of B, then they're independent. Or if they're independent, we know this, so we can make this substitution, and that's how we got this. But this only works if the events are independent. What's the difference between mutually exclusive and independent? Well, mutually exclusive is when there's absolutely no overlap. But independent just means that if the first event occurs, it does not affect the second event. Okay, we're going to explore this a little bit more in class. Media usage and good grades. In January 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people ages 8 to 18. In the study, 17% of the youth were classified as light media users, 62% classified as moderate media users, and 21% were classified as heavy media users. Of the light users who responded, 74 described their grades as good, while only 68% of the moderate users and 52% of the heavy users described their grades as good. According to the study, what percentage of young people ages 8 to 18 describe their grades as good? And we'll use a tree diagram to organize this. So we start off with 3 branches. We have light, moderate, and heavy internet users. The light media users were 17%. The moderate was 62, and the heavy was 21. From there, either your grades are good or they're not. Of the light users who responded, 74% said their grades were good, so 0.74, which means 0.26 said their grades were not good, because that has to add up to 1. Of the moderate, 0.68 said their grades were good, which means that 0.32 said they were not. And then of the heavy, 0.52 said their grades were good, which means 0.48 said they were not. What we want to know is all the people who describe their grades as good. So we have this branch, and this branch. All 3 of them said their grades were good, so all of those people need to be included. So this first branch would be 0.17 times 0.74, plus we would have this second branch, 0.62 times 0.68, and we would have this third branch, 0.52 times 0.21. And if we round this, that turns to 66%. We can rewrite the multiplication rule and get the following. Probability of A and B equals the probability of A times the probability of B given A. So what we're going to do is we're going to divide both sides by the probability of A. Because remember, that's just a number. So we get the probability of B given A equals the probability of A and B divided by the probability of A. This is our conditional probability formula. Notice how it's the same thing. You don't really need to memorize any formulas if you understand this one, and everything comes from it. Over 10,000 athletes competed in the 2008 Olympic Games in Beijing. The International Olympic Committee wanted to ensure that the competition was as fair as possible, so the committee administered more than 5,000 drug tests to athletes. All medal winners were tested, as well as other randomly selected competitors. Suppose that 2% of the athletes had actually taken drugs. No drug test is perfect. Sometimes the test says that an athlete took drugs, but the athlete actually didn't. We call this a false positive result. Other times, the drug test says an athlete is clean, but the athlete actually took drugs. This is called a false negative result. Suppose that the testing procedure used at the Olympics has a false positive rate of 1% and a false negative rate of 0.5. So we need to make a tree diagram to model the drug test. So our first branch was they actually took the drugs or they did not take the drugs. And then we need to see the test. So if they took the drugs, it should test positive. But if it tests negative, that's your false negative. If they did not take the drugs, that is your false positive. But if they did not take the drugs, that should be a negative. Now let's fill in the probabilities. So 2% actually taken the drugs. So 0.02 belongs with that, which means that 98% did not take the drugs, 0.98. Then from our drug list, we remember we had our false negative result, which was 0.005, which means that there is a positive drug test rate of 0.995. Then we had our false positive down here because they did not take the drugs, but it still tested positive. That's 1%, so 0.01, which means that the negative test 0.99. What's the probability that an athlete who tests positive actually took the drugs? We want to know the athlete took drugs given that they tested positive. What's hard to read about this, that I do every single year I teach this, is that the probability that an athlete who tests positive, so this is your given. So if we write our little formula, our conditional probability formula that we had from above, we have the probability that they took drugs and the test was positive divided by the probability that the test was positive. Using our multiplication formula, we can rewrite our numerator as the probability that they took the drugs times the probability that it tested positive given that they took the drugs out of all the probability that the drug test was positive. So now we can use our tree diagram to help us out. So we have the probability that they did the drugs, 0.02, times the probability that the test was positive given that they took the drugs, 0.995, all over the total probability that the test was positive. So this branch and this branch, so 0.02 times 0.995 plus 0.98 times 0.01. Putting this all into your calculator, you'll get something crazy. So we get a 67% chance that an athlete who tests positive actually took the drugs, which is kind of surprising. You would think that it would be a little higher than that. Then we'll use this table to do the same thing. We want to know the probability that an athlete who tests positive, so given that the test was positive, so we're only looking at this, actually took the drugs. So 199 over 297. So this is also 67%. But this was way easier, but that doesn't mean you're not allowed to know what this is. So if you can take these things and put them into a two-way table, I'm going to highly recommend that. But you need to know both. The tree diagram is sometimes more helpful.